3 and 1, 1 is less, so it will be on the left subtree. Now, if we check with 4 comma 5, we are dealing with different points here in the 2D plane. So we have the constructor. You will get the labels accordingly. Yeah, so you will get different labels. So we have a very small. Okay, so we are decently done with the front end now. So I have just sent the latitude and longitude onto this API, and in return I've got all the addresses and all the labels of those addresses. So this is the JSON file that is generated. We will make use of this. This is basically a database. So we will make use of this database, and we will try to optimize this database for searching, because there will be lots and lots of points over here, and to traverse all of these points is difficult. So basically this is a map which we have created, and in this map the latitude slash longitude string is generated, which is then mapped onto the uh, to the location that is being that we have to show up on the screen. Okay, so the problem that we are facing now here is that whenever we are clicking on any point, we see that location data is not available, and this problem will persist because we have up to we need the location that we are clicking onto. It should be equal to up to 6 decimal places with any of the string that we are matching with in the map. And if it is equal to those 6 decimal places for both latitude and longitude, then and then only there we will the application will return some valid label out, and that can be displayed over here. So to avoid that, what we can do is we can just find the nearest label available to that point. Let's say if we have this point, we will just calculate the nearest point which is available, and for that nearest point we will just see what label is available, and that label we can obviously display at the location place. So for that, what we will have to do is we will have to first of all, okay, so first of all, let's start here with the fact that we will have to just shift it to the backend, because it will take up a lot of searching which we don't want to do at the user end. So let's just push it onto the backend. I'll just use the fetch API. Okay, so I have already set up the backend, which is working on your port 8000. So in the backend, I've actually not added anything as of now, but it's simply the bootstrapped setup of the backend. So we will add some, let's say we have uh, the endpoint as reverse geocode, and we will add a latitude as a query parameter to this, and also the longitude as a query parameter. Yeah, so there you go. We have the latitude and longitude. I'll just add an await here, also an async here. Let's convert this into response.json. Along with that, let's access the json.label over here, and we will just change it to json.label. If json.label is present, okay, let's not do json.label, let's keep it label. No, never mind. So yeah, so this is how we are going to approach this. So the first thing is that we have multiple points, and in a real scenario there will be more than the points that we have. So if you just look at labels.json, we have so many points over here. We have almost 1500 points, and traversing along all these points to find the nearest point out of it and then getting the label is a very huge task, and it takes up a lot of time. So we will just optimize this a little bit, and that can be done using KD trees. So we will be using k dimensional trees in this case, and the dimensions that we have is 2. So we will be using a 2 dimensional tree that will help us traverse along this in an optimized format. We won't be now needing to travel along all the elements. We will just partition some elements out, and we will have to traverse along only a few of these elements to get to the nearest point. Okay, so what are these KD trees? So these KD trees are something of this sort. So you can just read it out here. Everything is present over here. So consider following points in a 2D plane, and in this 2D plane, we have to create some structure of this sort, so that whenever we are dealing with searching, the searching gets easier. Now, how does that get easier? I'll just show that in brief. So Okay, so first of all, let's say we have a point, let's say 3 comma 7. If you have a point called 3 comma 7, now whenever we are inserting into a KD tree, first of all we just insert I mean, if it's the first element, we will just set it as the root node. Now let's add another point which will be 4 comma 5, let's say. So if you have a point 4 comma 5, the first thing that the insertion function will check is the depth of the KD tree. So whenever an insertion operation occurs, I'll just write the algorithm over here. So the first step is that if we don't have the root, then we can simply create this new node. Create node. Next step is that it will just check. Okay, so first it will uh, calculate the what can we call it? It will calculate the, let's say, the dimension, let's say the dimension that has to be taken care of. So what is this dimension that we have to take care of? So first of all, we should note that whenever we have a KT tree of this sort, let's say this is a tree, and we will have some elements over here, then different elements to this. So this is basically the tree that we have. And in this tree, if we just look at the property of this, for every depth, for every level that we are dealing with, for every level there's a dimension that is taken care of. So if you look at this zeroth level, in this zeroth level, the dimension that we take care of is would be the x. So, and in the if we move forward in the level 1, the dimension that we will take care of would be y. And further down the line, if we go to the next level, the dimension that would be taken care of would be again x. So the dimension property here, so for dimension would always be equal to level percent k, which means we just have to take a modulus of level with respect to k. What will the modulus will return something, and that is the dimension that we will be comparing it with. So how it will go? If you just look at this, if when we are inserting 4 comma 5, the 4 comma 5, for 4 comma 5, the dimension would be 0 because it is at okay, so the dimension would be 1. Whenever we say, okay, so this is level 2, I'll just write it down. This is level 2 and this is level 1. Okay, this is level 0 and this is level 1. Okay, so we can do in any way. Never mind. I'll just take 0. I'll just start from 0. So when it is 0, we will check the x component, that is the 0th component. When it is 1, we will check one modulus of 2 because the amount of number of dimensions that we are dealing with is 2. So it is going to be a 2D tree. So when we take modulus of 1 with respect to 2, we get 1. And here we will be dealing with the first component or the component which is at the index 1, which would be y component. So here we check that 5 is less than 7. So if 5 is less than 7, it should be on the left of it. If we have some third point, let's say we have 1 comma 9. If we have this point here also, if we have to insert this, let's say we have only these 2 points in the tree, and now we have to insert the third point. Where will we insert that? So if you just look at the insert function, what it does is it calculates the depth. This depth is taken care of whenever we make a recursive call. Depth is increased by 1. It starts with 0. At that depth, we calculate the dimension. So yeah, it says current dimension, and we check the point of current dimension with that of the root. If it is less, we put it to the left. If it is greater than or equal, then we just put it to the right. This is how the KD tree will be formed. First, we will check the for okay. So first we will be at the root. At the root, we will check if the dimension is 0. So we will check with the 3 and 1. We will check with 3 and 1. If 3 is so if the dimension is 0, yeah, so we will be comparing the x dimensions. If x dimensions we are comparing 3 and 1, 1 is less, so it will be on the left subtree. Now, if we check with 4 comma 5, so any node that is going to be inserted in the tree, it will always be at the leaf node. It is just like a binary search tree. So here, if you just look at 4 comma 5 and 1 comma 9, the here the dimension will be modulus of 1 with respect to 2, that would be 1. We will check 5 and 9. If we check 5 and 9, 9 is the greater one. So we will place it onto the right child of the node. So in this way, we will construct the entire KD tree. Once we construct the entire KD tree, we will further look at how we can search in this. So we will first create a KD tree of this sort out of all the points. Once we create this tree, we can simply find the nearest point out of that, and once we get the nearest point, we will just simply return that label. So first of all, let's create this. For that, in the app.listen function, first I'll call generate kd tree function. So that will do for us. I'll just declare and start implementing this. For a kd tree, we also will require, let's say, we also will require a class that consists of all the functions and everything related to KD tree. In the backend itself, I will create a new JS file. It will consist of kdtree.js. So we will declare a class node. In this node, we will have a constructor. In the constructor, we will have this dot root equals root. When you have this dot left, then we will have null, and this dot right equals null. Initially, okay, so let's take it as a point because we are dealing with different points here in the 2D plane. So we have the constructor. Okay, so this is the class that we require. Now let's create some functions. Let's create a function called as insert. In the insert function, we will send a point. Uh, so we will call another function which would be insert root. So we are also having a root here, root comma point comma 0. Root point and 0. Let's also keep it as root. Insert into root, insert a point into root. Let's return uh, insert handler here. We will now declare the insert handler. So this insert handler is going to be a recursive function. Okay, so just the arrow. So if root is not present, we will simply return the new node. Then the next step would be we will calculate the dimension as level, so that this level would be the 0 and level percent of k is 2 because we have a two-dimensional thing over here, so that would be constant, and let's not play with that. Once we have the dimension, if we let's check for the condition. uh, so if we have the dimension as 0, we will check for latitude. We will need all the points. We will need this root, the point in the form of an array where we can access 0, comma 1 indices. So this is required that we will have to take care of while calling this function. And we have a const dimension is equal to level modulus of 2. Now, if we have point of dimension is less than root dot point of dimension, then let's insert it into left of the root. Root dot left equals insert handler of root comma point comma level. I'll just say root dot left of point comma level plus 1, else we will insert it into the right as insert handler of root dot right comma point comma level plus 1. So this will allow us to insert the things, and once it is done, we just return root. So this is how the insert handler function will work. Okay, so let's just export these functions, the class node and insert function. Now, once we have these, we will import it here. Const node comma insert equals require dot slash kd tree. That would be fine. Now in the generate KD tree function, first of all, we will have to get all the points that we have, and then we'll have to calculate everything based on that. So in the output.json, I feel like we have all the points. So let's just take output.json, paste it out here, and in this app.js, let's keep points as require dot slash output dot json. So we have all the points. Now for const point of points, every point we will start inserting into a root. I need that root to be here, let root. Okay, so if we just see, so I'll just say insert point, and the point has to be in the form of an array. So we say point dot latitude comma point dot longitude, and yeah, that should work. Once we start inserting in insert, we also send a root. Once we do that, mm, yeah, that should work actually. So if I, okay, let's not do anything to the root, generate KD tree. Let's see. Okay, so the server is running, but how can I just console.log root? So it says undefined root. Okay, so we are, I guess we are not assigning this to the root. Yeah, so that will create a difference. I'll just console.log root. Should see something. Yeah, so we have a point, then we have left, we have right, and yeah, so yeah, that looks fine. So for this, we have left as null and we have other points on the right. Okay, so the KD tree has been generated. We now have to find the nearest point for a certain point. So first, let's just declare this endpoint reverse geocode that will take up request response, and we will have latitude equals rec dot query dot latitude and const longitude equals rec dot query dot longitude. So this is how we will have. I'll just change something a bit in the app.js here. Latitude dot to fixed 6. We will do the same thing here as well. We won't send the entire thing. We will just send up to first 6 decimal places. Okay, so now that we have this, we have the latitude and longitude. Now the next part would be to find the minimum one in the entire tree. So for that, in the KD tree, we will have to declare a function const. Okay, so here we will, okay, so first let's declare the function here, const find nearest point to find nearest point. We will take a root as the argument along with that point as the argument. First, let's set the minimum distance to be okay, so let's set the minimum distance to be infinity. Okay, so now the problem is that for these values for a 2D plane it's okay, but when we are calculating Haversine distances, so in this case we take the curvature of Earth into consideration, because of which there are these sine and cos terms which are coming up. So that is why calculating any sort of distance is going to be a task over here. We just need to make complete use of these KD trees so that we can find it in the best way. So if you just look at how we can calculate distance for these simple 2D plane. For that, we can first we declare some min distance, which would be a huge value, let's say infinity. Now, the after that, whatever point we have on that node, we calculate the distance between between node and target. Once we calculate that distance, we set min distance accordingly, whatever will be the minimum one. Once the minimum distance is set, after that we can now we need to choose whether we have to go towards the left subtree or the right subtree. Now here is the decision making. So here it comes to be easier because we just have to take care of the dimension. Let's just take dimension. If the dimension is 1, and we just check, we just uh, subtract the components of that dimension, and if it is less than 0, we go to the left. If it is greater than 0, we go to the right. Yeah, so that is how we will do in a normal scenario. But in a so that split is something that is creating a difference. So we have a splitting axis. Whenever we are dealing with dimension as 1, we have y-axis as the splitting axis, which is creating that difference in a KD tree and which is making KD tree a KD tree. Now in this case, we can't use that y-axis or x-axis because we have a Haversine distance here. So I don't know if this will work, but that is what I've found out. Here we will first calculate a split point. So what is that split point? So this split point will basically be uh, will depend on the axis. If on the dimension, if dimension, so let's say if dimension is equal to 0, which means that it is working with x. If dimension is 0, what we'll do is we will get the latitude of node and longitude of the target point. So this will be the split point. And if dimension is 1, we will get the target latitude and node longitude. So this is the split point that we will be calculating. Now, why are we calculating this? I'm not really sure about that, but this is what I have found out. Once we do that, once we get the split point, so this split point is nothing but a representation of a split axis on the curvature of Earth. Okay, so once we have the split point, we will calculate the Haversine distance between the split point and the target point and the target point. So once we calculate this Haversine distance, if if this so this distance is going to be the split distance. So okay, so let's just assign it to be the split distance. Now, once we have the split distance, we can simply check if split distance is less than the minimum distance that we have obtained up till now. If that is so, if that is so, then we will simply if split distance is less than the minimum distance, which means that if you even go to the other node, I mean onto the other subtree, you won't get a distance which is greater than split distance. So we will not go there and we will simply return. Otherwise we will go to the other subtree. So this is the algorithm that we will be using, and I'm not sure about this part of split distance and checking the split distance, but it will most probably it will work and it will just help us to not traverse the entire tree. So that is what our main aim is, to not just traverse the entire tree. And obviously this condition will come into picture and it will obviously help us to not traverse the entire tree and do the entire operation with efficiency. So let's start here. Let's start coding this. So first of all, I have a minimum distance that is infinity. We also have to keep track of this minimum distance, right? So I'll just say, let's say a distance over here. It should be the nearest node that we are going to find. So first of all, I'll keep a track of minimum distance. That would be, it will first check if we have a node. If we do have a node, which means that it is not null, we will calculate the Haversine distance of the nearest node with the with the point f. Yeah. Okay, I can do this as well. Node of 0, node of 1. Then you have a point of 0 and point of 1. So these represent the latitudes and longitude. If not, then let's set it to infinity. Then we will also calculate the node distance. That would be Haversine distance of node of 0 comma node of 1 comma node of 0 node of 1. Then you have root dot point of 0 comma root dot point of 1. So this is the node distance. We will now check if if node distance is less than min distance, then we will update the min distance as node distance. Also, we will update node as the root dot point file, or else the node will be root itself. Okay, so these are the things that we have, and here also we will take this as point dot point. Now we have to create a split point. So that would be split point equal to, okay, so before creating the split point, we have to set the minimum distance. Okay, so the minimum distance has been set. Now we have to identify in which part of the subtree that this thing will I mean we have to check. Okay, so now in this, so here between set minimum distance and set split point, we also have to check which direction to go first. So that also we have to do. For that, what we will do is we will simply calculate the difference between the 2 points that we are dealing with. So we will first take difference is equal to node of, I'll say node dot point of node dot point. So we have this point as the target point. So point of 0 minus root dot point of 0. So that would not be point of 0, that would be uh, the level. So we have to keep track of the level modulus of 2, level modulus of 2. That would be the dimension that we are taking up. So the level would be here, that would start with 0, and that I'll call in the function itself. So this will be done. We will calculate the difference first. If difference if difference is less than 0, we will go to the left, or else we will go to the right. So first check const uh, priority sub3 would be if the difference is less than 0, then go to root dot left, or else go to root dot right, and const less priority sub3 would be if difference is less than 0, then go to root dot right, or else root dot left. So this is how we are going to do now in the priority subtree. Once we do this, we will first get the node, that is our final answer. Find nearest point. This is the recursive call to root dot left, root. Okay, no. So it would be in the priority subtree, and priority subtree, you have a point, you have a node, and a level plus 1. So that is the initial thing. Now we have to check if we need to traverse the less priority subtree as well. So for that we will create a split point. So we have a split point here. The split point will have this condition. So we will first calculate the Haversine distance. That would be the split distance. So first let's calculate the split point, and that depends on the dimension. So first let's check if level equals 0, then we will set the split point as node.lat, target.long. We will set it to be, if level is 0, then we will set it to be on node, that is root dot point of 0, comma point of 1, or else we will set it to root point. Okay, so it will be point of 0, comma root dot point of 1. So this will be the split point. Let's also calculate the split distance. That would be Haversine distance of split point uh, with the target point. Split point of 0, comma split point of 1, comma point of 0, comma point of 1. So that would be the Haversine distance. Split distance is equal to Haversine distance. Now we have the Haversine distance. Now we will simply compare split distance if it is less than minimum distance. So let's compare that. If split distance is less than minimum distance, then we can find something over here. Then we won't find anything over here. So if split distance is greater than minimum distance, we will simply call this function find nearest point for the less priority subtree with point, node, and level plus 1. Okay, so that should do for us. So for that, we will export this function find nearest point. Once we export this, we will just get this out here. Once we have this, we will have a latitude and longitude. For that, first we will what we'll have to pass is the route. Then you have a okay. So let's see const nearest point equals find nearest point of route comma point. So this point okay. So let's keep it point. Then you have level that would be starting with 0. We will have to create this point. The point would be point would simply be an array. Yeah, so it would be an array where you take number of latitude dot fixed of 6, and similarly for the longitude as well. This will be the longitude. Okay, so we have this function. We get a nearest point. I just need to rest first. Let's just send a 200 rest dot send message success. Let's do this for now, and I will also uh, print this nearest point over here. Let's see if that works or it creates a problem. So we have a reverse geocode. Cannot read properties of undefined kd3.js of 46. Okay, so here we have something that is not working. Mistake here. Fine, that looks fine. Okay, so I think the root, if not of root, then return point, right? Okay, so if not of root, return node, which would be our base condition. So the message now is success, and this is fine. Now let's see what the nearest point it gives. Yeah, so it has given us a nearest point, 28.64295. Yeah, it has given us the nearest point, which is itself. Yeah, so this function is working. The nearest point function is working. I will just add a try catch over here. Const nearest point, and let's just res dot status of 200 dot send label as the label of this nearest point. So that would be nearest point dot point nearest point dot point, and I'll have to search that in the labels. So do I have label.json? No, I don't have that. I'll just copy this and paste it here. Now I'll just import the const labels equals require dot slash labels. We have the label. Now we will just say, okay, so we'll have to also get that string here. So for that, okay, so we have the nearest point. The nearest point is fine. Now for the nearest point, we will create the string. So const key string equals uh, nearest point of point nearest point dot point of 0, yeah, slash nearest point dot point of 1. So this would be the key string. Now I'll return response where I will send a label that would be mm, labels of key string. So that should work. If not, then let's catch the error and rest dot status of 500 dot send error message as error dot message. Yeah, so that should work. Yeah, the label is coming out to be fine. So we have used KD trees here. The KD trees thing is working, and the labels that we are getting is also working. Yeah, so this is working now. The KD trees part is working. We are getting labels here. Now let's check if that is working on the map. Yeah, on the map also it is working. If you click on any point, you will get the labels accordingly. Yeah, so you will get different labels. So we have a very small area over here due to which we won't get to see many different labels, but yeah, fine. So whatever we are getting is quite okay.